Hello. If you are tuning in on Ether Cosmology, please bear with us for just a moment here. I'm waiting for Alan's intro to finish over on Space Audits, and then we will begin reading.
Looking for a quick lunch break that doesn't break the bank? Black Rock Bar and Grill has you covered for...
Hey there, I'm Albert Clownstein. Welcome to my special circus.
Have you ever heard of a circus where math equations are as exciting as the clowns?
Excellent. Thank you, everyone, for being here, for tuning in to Reading Night at Ether Cosmology, Reading and Research Night, where we do live research on the spot. This is not us giving a presentation to you, but rather us literally doing live reading, live research. And in the special case of tonight and the last couple of weeks, we have been reading a physics textbook, or it's an advanced physics textbook. It's from Shankar. And so we've been getting into that at the request of some people on the server here. And tonight, though, we are going to deviate that from just a little bit, and we're going to read a paper that was shared with us, and then we're going to get back into the physics textbook. We're on chapter 4 of Shankar Physics 1, and but first we're going to read this paper from Ramzi Suleiman, as well as Kari, Kushi, and
the boys.
And Abu dies. So there you go. Or wait, no. Can't find the
Spoiler.
names. Dude, it's hard to find the names. Okay, there we go. So I think I had it. Kari, Haifa, dies. Something like that. Ramzi Suleiman, thank you for your paper. The Sagnac effect falsifies special relativity theory. This was shared with us a couple days ago by Robert Bennett. To him, we are grateful for sharing his knowledge. So, abstract. It is believed that the Sagnac effect does not contradict special relativity theory because it is manifest in non-inertial rotational motion. Therefore, it should be treated in the framework of general relativity theory. However, several well-designated studies, important distinction there, so he's saying it does not contradict special relativity because it needs to be treated within general relativity. That's why. In case you missed that distinction.
Yeah, and we'll come back to that in a bit. That with the polygonal loops or closed polygonal circuits, because it's like, where do Einstein's equations apply? Everyone seems to think that a uniformly rotating device in rotation doesn't apply to special relativity, but we'll go back to the Holy Scriptures and see if that's true or not. So anyway, please continue.
Cool. Yeah. So. However, several well-designed studies have convincingly shown that a Sagnac effect identical to the one manifest in rotational uniform motion is also manifest in transverse uniform motion. Thanks, Wong. This result should have been sufficient to falsify special relativity theory. Indeed. In the present article, we offer theoretical support to the experimental results by elucidating the notion that the dynamics of transverse and rotational types of motion are completely equivalent. Since the transverse Sagnac effect contradicts special relativity theory, it follows that the rotational Sagnac effect contradicts special relativity theory as well. Well said. Well said. Like, that's kind of why it's like you guys lost your get out of jail free card when Swang did his thing in 2004.
Shout out to Wong.
In addition, we show that our recently proposed information relativity theory, oh boy, in which we abandon the constancy of the velocity of light axiom, nice, theoretically accounts for the Sagnac effect.
Oh, so if you abandon the core postulate that makes relativity theory,
We're just going to keep calling it relativity.
You can what? Dude, the amount of backflips and hurdles that have to go on.
It's going to be like This is called substantive medium relativity. You know, everything is like literally a substantive medium in the background. It's not ether, definitely not ether. And the only thing that's different from it and ether is that you can't measure orbital velocity.
Of Earth. All other orbital velocities are measurable.
Yup. All right. The Sagnac effect, called after its discoverer in 1913, citation 1, has been replicated in many experiments. It is well known that the Sagnac... Okay, actually, I just want to take a little peek at that. Since we got a 4-pager anyways, we might as well hop on down and take a look at citations 2 through 5. So, has been replicated in many experiments. Wonder which ones he's talking about.
Let's see. So 2, we got Ashby. So relativity and rotating frame. So that would be the Sagnac effect in GPS.
Okay.
We got Post and others. I forget who that is in regard to, but I think it may be also a GPS thing. We have Anderson, Bilger, and Stedman in the Sagnac effect. So these are the lads that did the Michelson, Gale, Pearson in the South.
Oh, nice.
And then we have Malikan in the studies of the Sagnac effect. Not familiar with that one. And we got Ashby again with the global positioning system and the Sagnac effect. So lots of rotating systems and lots of variance in the speed of light. That is not our boy.
Oh no, that's WW. My bad. My bad. I mean, he could be cool too, but
he's definitely cool, but he's not our boy.
Gotcha.
Yeah.
All right.
Scroll down a little more.
Oh.
Hold on. I saw another one I recognize. My boy, Luganov. That guy. We'll definitely have to take a look at what he has to say about the Sagnac effect. And then we got Wang at the bottom. Cool. So a bunch of analysis.
The 2003
Sagnac effect.
Go ahead. What up, Bennett?
Yeah, I just wanted to jump in. There's tons of Sagnac applications, probably in every airplane you take, every ship. All of them use that for navigation. So besides the technical documents, there's plenty of physical applications in technology. And although they apply it, they really don't understand how it works. Not at the ether level, certainly.
No, certainly not at the ether level. In the mainstream documents for inertial navigation systems, they teach it as so. In this paper, they're saying it's definitely treated as special or general relativity, but how they teach it in the inertial navigation documents, they just teach it as special relativity, and they invoke the geometrically convenient position of the center of the rotating apparatus, and then with respect to the the edge of it is the what they're measuring, and then they say it's just a time difference between the outer rim and the stationary center lad. It's crazy. But yeah, they teach it as a special relativity effect.
All right, let's keep on reading, I suppose, here. Unless you had any other thoughts, Robert?
No, go ahead, Toby.
Cool. It is well known that the Sagnac effect has crucial applications in navigation and in fiber optic gyroscopes. In the Sagnac effect, 2 light beams sent clockwise and counterclockwise around a closed path on a rotating disk take different time intervals to travel the path. For a circular path of radius r, the difference can be represented as delta t equals 2 VL over c squared.
Nu.
Oh, that is mu? Okay.
Nu.
My bad. Nu. 2 nu L over c squared, where that's still nu?
Yep. Nu omega.
Nu equals omega. R is the speed of the circular motion, and L equals 2 pi r is the circumference of the circle. Today, fiber optic gyros have become highly sensitive detectors for measuring rotational motion in navigation. In the GPS system, the speed of light relative to a rotating frame is corrected by plus or minus omega r, where omega is the radial velocity of the rotating frame, and r is the rotation radius. A plus-minus sign is usually used depending on whether the rotating frame is approaching the light source or departing from it, respectively. It is claimed that the Sagnac effect does not contradict special relativity theory, since it is manifest in rotational motion, which is considered an accelerated motion. Thus, the effect should be treated in the framework of general relativity. Despite the above-mentioned claim, a correction for special relativity's time dilation is still implemented in GPS system, alongside with a rotational Sagnac correction. More importantly, the findings of well-designed experiments contradict the aforementioned claim by demonstrating unambiguously the light or the effect manifest in rotational motion, which is identical to Sagnac effect, is also manifest in transverse uniform motion. The manifestation of a Sagnac effect in the latter type of motion should have raised very serious doubts about the validity of special relativity's second axiom. However, given its central place in all physics, the aforementioned axiom continues to be a quote-unquote untouchable exception that defies falsification. On the equivalence between transverse and rotational dynamics. In this article, we give further support to the experimental refutation of special relativity by restating that the theoretical descriptions of the dynamics of transverse and rotational systems are identical, implying that the two types of motion are completely equivalent. In systems sciences, the equivalence of two dynamical systems implies that their mathematical descriptions must be indistinguishable. On the one hand, the dynamics of a transversely moving body is completely described by the variables t, time, x, distance, nu, transverse velocity, mass, f, force, and their interdependencies, as formulated by the laws of transverse motion. See the left side of column in Table 1. We'll get to that in just a minute. On the other hand, the dynamics of a rotating body is completely described by the variables t, time, theta, angular position, w, angular velocity, or omega, angular velocity, I, radial inertia, and tau, torque, and their interdependencies as formulated by the laws of rotational motion. See the middle column in Table 1. A short inspection of the table reveals that the two sets of equations are equivalent. A general representation of the two systems is depicted in the right side of Table 1. Confronted with the set of equations appearing on the right side column of the table, we will have no way of knowing whether the system's parameters, pi, and their interdependencies represent a system in transverse or rotational motion. Note that in the table, we did not specify that the parameter p1 should be represented. All right, let's look at the table real quick here. So we've got translational, so the generalized effect in linear motion, radial, and then, so this must be like the
Dude, this is
generalization
great.
of the two.
This is like the breakdown of that rectilinear paper where they were talking about the different types of motion and all the math that describes them is all the same. So like breaking them up into different types is kind of, R-worded, as Dude said earlier.
Yeah.
Almost like Cartesian simultaneity.
Oh yeah, Cartesian simultaneity. Yeah, essentially. Because it's like, okay, there's an absolute space for the rotational, but not for the transverse. Even though it's described exactly the same, and there's and the only way that you couldn't describe the transverse is if you remove an ether to have the motion be relative to that. So you're just like, oh, I don't know, it doesn't exist. Absolute stars? I don't know.
Yeah, so straightforward. All right, so note that in the table, we did not specify that the parameter p1 should represent position, that the parameter p2 should represent velocity, and so forth. This is because any physical, biological, or other dynamic system with the same set of parameters, pi, and the same interdependencies described in the right side column on Table 1 is equivalent to the two systems of motion discussed here. If the reader is convinced that, in general, the transverse and rotational systems are completely equivalent, then the equivalence between the special cases of uniform motion with constant velocities nu and omega, respectively, follows as a corollary. It follows immediately that the claim that the rotational Sagnac effect does not contradict special relativity is a false claim. Word. Another indirect support for our claim that the Sagnac effect contradicts special relativity theory is the fact that the Sagnac effect can be derived theoretically from our recently proposed information relativity theory. Oh, yay. In which we abandon I'm all for abandoning the second axiom. In which we abandoned the second axiom of Einstein's special relativity for a transversely moving detector with a velocity nu relative to light source. That's certainly that's very against SR.
That's certainly abandoning the old axiom.
It's like literally abandoning the kind of the keystone of the whole thing, but okay. Wow. Well, that's oops,
Maybe we should go back to when Toby started and said that there's a conflict even among mainstream folks about whether an accelerated system belongs to special relativity or not. When you're rotating, you're not moving in constant linear motion, which is one of the postulates for special relativity. And so there's a group in mainstream who say that special relativity does not apply to accelerated systems. And yet, Big Al himself said that if we consider a polygon of n sides, and we let the number of sides go to infinity, then the polygon becomes a circle. And if you apply special relativity to the polygon, it works because it's a series of straight lines. And if you ignore the time loss in changing direction when the edges come together, then Big Al said, yes, the circular motion does belong to special relativity. What's interesting is I tried to save this quote from Einstein. I lost it, and then I tried to search for it again on the internet. I couldn't find it. So I don't know if there's anything nefarious going on here, but it's interesting that even to this day, there's a group that says circular motion does not belong to special relativity. You must use general. And there's others that say, yes, it does. So they can have it both ways, apparently, and there's no logical contradiction. Such is the world of special relativity.
Yeah. I got it. One quote up right here from his 1905 paper, and then there's another one sourced from like a series of writings that him and Lorentz did, where he makes it a little more clear. But yeah, reading from the 1905 paper in regards to where his equations apply, he says, and if a clock at A is moved with a velocity of nu along the line AB to B, then on its arrival at B, the two clocks are no longer synchronized. But if the clock moved from A to B lags behind, and the other, which has remained at B, by 1/2 times t nu squared over c squared, t being the time occupied by the journey from A to B. And then it says, it is at once apparent that the results still hold good if the clock moves from A to B in any polygonal line, and that when the points A and B coincide. And if we assume that the results proved for a polygonal line is valid, then it is also valid for a continuously curved line. And we arrive at these results. And he goes on to talk about the time difference that the clock will experience due to his equations being valid in that uniformly rotating frame.
Excellent, Alan. You found it.
Thank you, good sir.
Yes. Yeah, that's exactly what I was looking for.
Yeah, it's the one piece of Einstein's 1905 paper that makes logical sense. Where it's like, if you like you were saying, if you extend any parts of the polygon to infinity, it's a straight line. Especially if it's a circle, then you're really a straight line, and there's not going to be any deviation. So you definitely should apply in there. And then so to separate this issue, right? Because if there's an absolute fixed space for a rotation like that, well, if the Earth is going around the sun, Well, there's going to be a fixed point for that to be relative to as well. And there's going to have to be a velocity component measured in there. So they had to get rid of that as well, and then wrap up the whole situation as general relativity. And so, because if you take the rotating device, right, a local rotating Sagnac apparatus, it's not going to be rotating fast enough for your boy Lorentz symmetry to matter, to produce link contraction and time dilation, to produce the fringes, because you got to remember the speed of light's going at the same speed for an inertial observer. So there's not going to be a fringe pattern unless the apparatus itself is physically changing, but that's retarded under the confines of special relativity. So they come in with GR and they say, okay, bet we can now conserve the entire energy of the rotation of the device into a little gravitational field and invoke that as a link contraction time dilation 1-to-1 of the device's rotational speed, even though it's not traveling at relativistic speeds. Very convoluted, but super necessary for them.
Yeah. It seems like general relativity is the garbage can. Like, if special relativity can't handle it, well, we'll throw it into general relativity, which is like a black hole. And in a theoretical black hole in which, it explains everything, but its math, unfortunately, makes no sense. So that's the world that science is at now, where it's either special relativity or general relativity that can handle anything, and it's either one or the other. Yeah,
Yep.
that's excellent that you found that the quote. Where is that?
So the first one is in his 1905 on the electrodynamics of moving bodies, and then the other one I have in a. Let me see if I still have it. Let's see if I can find it, because it's like even written a little more clear, because you know how they do the old translation of the old English language. But this one was written a long time ago. Let's see. Yeah, I'll look for it later. You ready to continue, Toby?
Okay, or you can send me an email.
Oh yeah, for sure, if I find it.
Yeah, we can definitely reach out. Cool. I will continue on then here. So, for a transversely moving detector with a velocity nu relative to light source, the theory prescribes that the time duration as measured by the detector of an event with a duration delta t prime taking place at the light source is given by the following Doppler-like formula. Delta t equals 1 over 1 plus or minus v over c times delta t prime, where the plus sign applies when the detector approaches the light source and the minus applies when it is moving away from the light source. For a path of length L, we have delta t prime equals L over C. Substitution in equation 1 yields delta t equals 1 over 1 plus or minus v over c. L over c equals L over c plus or minus v. The difference between the arrival times of two light beams propagating in opposite directions along the same path is given by delta t equals c over c minus v minus c over c plus v times L over c, and that's going to equal c plus v minus c minus v over c minus v times c plus v times L, which equals 2 times v times L over c minus v times c plus v, and that equals 2vl, which equal over 2vl over c squared minus v squared, which is approximately equal to 2vl over c squared. The above result is identical to the formula which describes the rotational and transverse Sagnac effect. Summary and conclusions. It is commonly accepted that the manifestation of the Sagnac effect in rotational motion does not contradict special relativity, since the latter applies only to transverse uniform motion and not to rotational motion, which involves acceleration. The fact that a Sagnac effect identical to the one manifest in rotational motion was also detected in transverse uniform motion strongly refutes special relativity theory. However, given the central role of the theory's second axiom in all of physics, the above-mentioned results concerning the existence of a Sagnac effect in transverse uniform motion has been until now widely neglected, still quite neglected, sadly. In the present paper, we provided further support to the experimental refutation of special relativity by showing, theoretically, that the transverse and rotational types of motion are completely equivalent dynamic systems. In principle, we elucidated the fact that when the set of equations describing the interdependencies between the variables of a rotational or transverse dynamic system are written using a set of uniformative symbols, pi, I equals 1, 2, iterating up to n, then we will have no way of knowing whether the system's parameters and their interdependencies describe a transverse or rotational motion. Accordingly, it follows that both the rotational and transverse types of Sagnac effects contradict special relativity. If we accept the principle that theories are falsified by contradictory empirical evidence, then special relativity's second axiom must be abandoned, no matter how dramatic the consequences might be.
All right, so heads up, boys. The consequences of abandoning special relativity is that the Earth is stationary. So that's the
Is there
stipulation.
ever any reference to Wang, the Wang experiment?
There was early
Yes.
on.
Yep. Yeah.
That's actually. I
citations.
think that was the main. Or interestingly, the only reference to Wang is the 2003 paper, and that was citation 17. So I don't think he did get to it till a bit later on.
2003, I don't think was the.
That was the first
key
time he did it.
experiment.
That was the one with the figure 8 configuration and the a few other configurations along those lines. It was the first time he did it. It was, I can't remember what the exact title of the paper is. It is
Yeah, the key
Yeah,
one is the one with the graph, the straight line graph, which shows
Mm.
that linear motion produces this a linear phase shift.
Yep,
And
that's the 2004 one, and then
I think it's the 2005.
well, so
paper.
2004. So you have modified Sagnac experiment for measuring time, travel time difference. Let me open the paper. Modified Sagnac experiment for measuring travel time difference between counter-propagating light beams in a uniformly moving fiber. So this was the first time they did it. And then it was actually before even... So after this paper, after they released this paper with these experiments, he filed the preliminary patent work for his speedometer. And then after that, then they did more experiments and they published the generalized Sagnac effect. And that was in 2004.
Yeah, he has a patent for I think millimeters per second, something like that. Very low speed objects can be detected with the Wang application. Hurdle speed.
I mean, you can detect your position in absolute space with interferometry without accounting for, or just by abandoning special relativity. That's all you have to do. Just acknowledge the measurements for what they are. I don't know. It sounds too easy.
Well,
Very unscientific.
you set up an interferometer on a moving platform, just like the what was it called, the glider
Yeah, the Wang. Yeah, it's conveyor belt.
in the Wang experiment, and then you try and detect what is the lowest speed that I can detect, And since you're using wavelengths of light, I mean, it's even smaller than millimeters per second. So it's for measuring very low speeds, although it can be applied to any speed.
Nice. Yeah, that's going to give you an insane amount of precision on that when you're down at those millimeter wavelengths.
At the end?
So yeah, that was all of that paper. Now we were gonna jump back into the Shankar physics book. We are on chapter 4, more of Newton's laws. Should I go ahead and get us started with this one?
Yeah. Popcorn me in whenever you're ready.
Cool.
Likewise, popcorn me in whenever you're ready too.
Yes, and by me I meant popcorn Scott in.
Awesome. All right, I'll get us started then. So, section 4.1, a solved example. The goal of physics is to be able to predict something about the future, given something about the present. I'm going to provide a very simple example that illustrates how Newton's laws are to be used for this purpose. This treatment will be brief since I will return to this problem in greater detail later. Figure 4.1 shows a frictionless table in which a mass m attached to a spring of force constant k. The other end of the spring is attached to an immobile wall. The dotted outline of the mass shows it when it is displaced by an amount x from equilibrium. I want to pull the mass by some amount a and let it go. So that's the knowledge of the present. What's this guy going to do? That's the typical physics problem. It can get more and more complex. You can replace the mass by a planet. You can replace the spring by the sun, which is attracting the planet. You can bring in many planets. You can make it more and more complicated. Can you? Are you sure about that? But they all boil down to a similar exercise. I have some information now, and I want to be able to say what will happen next. So there you go. A mass m attached to a spring of constant force k in its equilibrium position when the spring is neither extended nor compressed. The dotted outline of the mass shows it when it is displaced by an amount x from equilibrium. Combining F equals ma and F equals negative kx, we obtain the equation that seals the fate of the mass. So the second derivative of x with respect to t equals negative k over m times x of t of x, x of t. This is a differential equation. You have to find a function x of t whose second derivative is negative k over m times itself. A differential equation tells you something about an unknown function x of t in terms of its derivatives, and you are supposed to find it given this information. Instead of running to the mathematics, let us solve this equation by guessing, which is a totally legitimate way to solve a differential equation. Here's how we guess the answer. Let's make our life simple by taking a case where k equals 1, m equals 1. Later on, we can put back any k and m. I'm looking for a function whose second derivative is minus that function. Now, as a word problem, it rings a bell, right? Do you know such a function? Exponential is good. Trigonometric functions are good too, provided you mean sine and cosine. I'm going to dismiss the exponential, which is actually a very good guess. If you took x of t equals e to the power of t, we have the second derivative of t equals e to the power of t, which is not equal to negative x of t. T of negative x. It does not help to consider t of x equals e to the negative t, since the minus sign will get squared when you take two derivatives. And you will still end up with plus t of x, or plus t of plus x. Now, e plus or minus it, or e to the power of plus or minus it, where I equals the square root of negative 1 will work. But we do not want to deal with complex numbers yet. We just want a function that reproduces itself when we take two derivatives. So I make a guess. T of x equals the cosine of t, and you can check that it works. So we have our second derivative equals the, so we're taking the cosine of t. I actually don't know what's happening here. How we're going from, so we're,
Should be sine of omega t.
yeah, shouldn't that be different, literally? That seems odd to me. But in any case, I will keep reading. Did you follow the way this? What's up?
Well, just what's the derivative of cosine again, Mr. Bennett? I mean
The sine of the, it's either plus or minus the sine.
and then when you take the derivative of the sine, would that be negative
You get the
cosine?
cosine again.
Oh, well,
but
there you
with the
go.
minus.
Okay. Aha, that makes sense then.
Which equals negative x of t. I mean, because they chose that to be cosine of t.
That makes sense now. Thank you. Thank you. Thank you. So it's just because it's a second derivative. Okay. Did you follow the way this very elementary problem is solved? I did, thanks to Bennett and Scott. It's solved by making a guess, but something is not quite okay with this solution. If I put t equals 0, I get x equals 1. Why should it be true that I initially pulled it by exactly 1 meter? I could have pulled it by 2 or 3 or 9 meters. I want to be able to decide how much I pulled it by at t equals 0. Suppose it was pulled to 5 meters and released. I want 0 of x to equal 5. This can be arranged by making a choice. T of x equals the 5 times the cosine of t. Popcorn Scott?
Okay. Yeah. Pardon me. Does the 5 screw up everything? It doesn't, because it just comes along for the ride. So the second differential of
fuck
x
is that?
What, the 5? Was there a question?
No, you're good. Sorry about that.
All right. What's that? Oh no, that's cool. So does the 5 screw up everything? It doesn't, because it just comes along for the ride. So the second differential of x with respect to time equals the second differential of 5 cosine of t taken with respect to time, which equals negative 5 cosine t equals negative x of t. So it's exactly what he said. The 5 doesn't cause any trouble. So now I have an answer that does everything I wanted to do. At the initial time, it gives me 5 times cosine of 0, which is 5. And that's what I said was the initial displacement. I find dxdt equals negative 5 sine of t. So there's the single goes to sine, which vanishes at t equals 0. That too is correct. I pulled it and let it go. So the instant I released it, it had no velocity. It satisfies Newton's laws, and that's the answer. I want to do this simple example in totality because this is the paradigm. This is the example after which everything else is modeled. There are 2 final points about this solution. First, there's the other option, x of t equals sine of t, that occurs to some students. There's nothing wrong with this option. It just is not needed in this particular example. Equation 4.5 is not the final and most general solution to the problem. It is a solution that certainly works for the one example I had, in which a mass is pulled to 5 meters and released. Second, when k and m are not both 1, we go back to the general case. The second differential of x with respect to time equals negative k over m x of t. Solution to this is x of t equals a cosine the square root of k over m times t. Or actually, yeah. Where a, which was 5 in our example, is arbitrary in general and is called the amplitude. We'll deal with the oscillator in depth later. At this point, we just want to get a feeling for how F equals ma is applied in real life, with some help from the mathematicians. 4.2, never the whole story. Is this the whole story of the mass and spring, or is something missing? Does the mass oscillate forever as predicted by the equation 4.1 we just solved? It does not. It eventually comes to rest. If you never knew about friction and you solved for x of t with just the spring force, you would find it didn't work. You're at a fork in the road. You can say either that Newton's laws are incorrect or that you're missing some forces. In the latter case, you will look around and eventually deduce the frictional force by insisting that F equals ma works with its inclusion. We will show how this is done later in this chapter. It turns out that even if there were no friction, equation 4.1 would not be the correct law, which is given by Einstein's relativistic dynamics. By that, I mean, if you really, I just feel a little odd that the relativistic dynamics, I mean, we're looking at a spring. I don't know where relativistic dynamics got involved.
Dude,
By that, I mean,
He's
if you
saying
really,
Go ahead.
he's saying if the speed approaches c, then you have to consider relativity in the motion of the oscillations of the spring.
okay,
Mm.
That,
fair enough.
that's the mainstream argument. Yeah.
By that, I mean, if you really pull a real spring by 5 meters on a frictionless surface and release it, its motion will not be exactly 5 cosine t. It will be off by a very, very, very tiny amount that you probably will not discover in most laboratories. If the mass begins to move at a velocity that is comparable to that of light, here we go, then this equation will make the wrong predictions. On hearing that even Newton can be wrong in this sense, some people say, what kind of business are you in? Every once in a while, some authority is proven wrong. Yeah, aren't they? I'll tell you right now, everything we know is wrong at some level. This is interesting. Newton didn't try to describe things moving at speeds comparable to light. He dealt with the problems he could deal with at that time. So his laws have a limited domain of validity. You can always push the frontiers of observation until you come to a situation where any given law breaks down. While the
Yo, can you
special theory of
highlight that
relativity
domain
does
of validity? The domain of validity stuff real quick. Can you highlight that?
right, so his laws have a limited domain of validity.
Yeah, like where these equations apply, etc. Very important.
Got it.
But it's funny, this is a very frank discussion about it all that we never receive. You know, the equations are infallible when we're trying to, discuss this stuff with globers, so to speak.
So true.
Right.
Yeah, here they're being honest. While the special theory of relativity does better than Newtonian mechanics for large velocities, it too fails if the mass becomes very tiny, of atomic dimensions. Then you need the laws of quantum mechanics discovered by Heisenberg, Dirac, and Schrödinger. And of course, their laws also have problems in some experimental domain. Sometimes we correctly abandon the formalism, but we should not be too eager to do that. In the present case, the problem is not with formalism, but with not including friction. The failure at the quantum level comes not because we did not include some forces, but because the very notions of force or trajectories, x of t, seem to be invalid at that scale. I'll keep going if we're cool with that.
Absolutely.
Yeah,
Okay.
you're great with me. Whenever you're done, ready to be done, you can send it back over or whatever.
Okay, cool. I'll just keep going for a bit. 4.3, motion in d equals 2. We're going to move on to higher dimensions where position, velocity, acceleration, and force are all vectors. So let's again start with simple problems in d equals 2 dimensions, and make them more and more complex. There is no limit to how difficult mechanics problems can be. If you go back and read some Cambridge University exams from 1700 or 1800, you will find some really difficult problems. Finally, quantum mechanics was invented, and life got a lot easier.
I don't think that's true.
Yeah, on several levels, that seems false. Consider a mass m sitting on a table as shown in the left half of figure 4.2. Because we're in 2 dimensions, we need to have 2 axes, x and y. Recall that. So, recall that I was looking at the picture there. a mass M sitting on a table on the left without and on the right with friction. The coefficient mu equals mu S if the block is at rest, and mu equals mu K if it is moving. So is a vector equation. If two vectors are equal, then their x and y components have to match. So the force in the x direction has to equal m, and the acceleration in the x direction, and the force in the y has to equal m a y. I'm going to apply them to this block. There are no known forces acting in the x direction, and the block is not moving in that direction. Therefore, it's a case of 0 equals 0. Now I look in the y direction. In the free body diagram, there is the force of gravity, mg, acting down the y-axis. I will often denote this vector by mg, where g, which is a vector going down, is gravity, negative 9.8. What is that? Oh, joule meters per second squared? Or what's that j?
It'd be meters per second squared.
Yeah, why is that j there? Like it says negative 9.8 and then like a vector j, m meters per second squared.
Okay, let me just say, J is the unit vector pointing in the y direction.
Oh, okay, right. We actually went over that before. If that's all you had, the block would fall through the table. Because the block is not falling, we know the table is exerting an opposing force denoted by n, where n stands for normal. And normal is a mathematical term for perpendicular. Evidently, n is a positive force and mg is a negative force in the y direction. Thus, n minus mg equals m times the acceleration in the y direction. You good? In this application of the Newtonian equation, I know the right-hand side. It is 0 because I know this block is neither sinking into the table nor flying off the table. It's sitting on the table. It has no velocity or acceleration in the y direction. I come to the conclusion n equals m times the acceleration due to gravity, mg. 4.4, friction, static, and kinetic. Now I'm ready to introduce another force, the force of friction, F as a vector. How do we infer there is a force of friction? Consider the mass on the table in the right half of figure 4.2. What experiment will tell you there is another force called friction? You find that to keep the mass moving at constant velocity, you have to apply a force. That means the force you're applying is canceled by something else because there is 0 acceleration. Here is another good answer. You give the mass a push and soon it stops moving. There must have been a force that produced the deceleration. But even before that, even before it starts moving, you find that if you push it, it doesn't move. See, I push the podium. If I push it gently, it does not move. But if I push it hard enough, it begins to move. What's happening before it moves? I'm applying a force and I'm getting nothing in return for it. So I know there's another force exactly balancing mine, and that's the force of static friction. Let us call the force I'm applying F equals ME. I'm applying it to the right, and so there has to be another force of equal magnitude to the left. Notice it is not a fixed force. It's whatever it takes to keep the mass from moving. It will not be less than what I apply, because then the mass will move. It cannot be more than what I apply, because then it will start moving me backward. So static friction is a force that has a range from 0 to some maximum. Maximum turns out to be the force of friction equals mu s times n, where mu s, that is mu, right?
Yep.
Okay. Where mu s is a number called the coefficient of static friction, and n is the normal force. In our example, you may use n equals mg. So the force of friction seems to depend on how heavy the object is that's sitting on the table, but it doesn't depend on the area of contact. For example, it does not increase if we rest the block on another face with greater area. You might expect more friction because there's more contact, but that is not so, for reasons not readily explained within our elementary treatment. In reality, friction has a subtle origin at the atomic level. If static friction provides a force equal to the force that I apply up to a maximum of mu s times n, what happens when I exceed the maximum? the object I'm pushing will start moving. Once it starts moving, the frictional force, which is always directed opposite to the velocity, changes to F of k equals mu k n, where mu of k is the coefficient of kinetic friction. We find that in all situations, mu of k is less than mu s. Let us say mu s equals 0.25 and mu of k equals 0.2 for the block on the table. If I apply a force that is 0.1 times its weight, it won't move. At 0.2 times its weight, it won't move. At a quarter of its weight, it's a tie. At 0.26 of its weight, the block will start moving. Once it starts moving, the frictional force will drop to 0.2 times its weight, and the body will accelerate if I maintain the same force as when it first begins moving. So I'm still up for going, but just wondering are we all good there?
Is anyone interested in the atomic explanation for friction? A
Yes.
microscopic description, which he skipped.
Yeah.
Okay, if you take a smooth surface, like a desktop, which looks smooth, or even glass, anything that looks smooth, and you examine it at microscopic levels, you'll find that it's really like the surface of the Earth, in that it has hills and valleys. There's piles of atoms in some places, and then there's valleys in other places. So when you put two surfaces together, what you're really doing is forcing the hills in on one surface into the valleys on another surface. Okay? And then when you try to move it, which is what he's talking about, the overcoming static friction, what you have to do actually is chop off some of the mountains at the microscopic scale, the atomic mountains. And that's what is causing the resistance. Because it isn't perfectly smooth, although it appears to us at our level of vision that it's a smooth surface. All surfaces are basically, unless they're very precisely machined, they all have these hills and valleys. So static friction is overcoming the hills and valleys, actually chopping off some of them so that the two surfaces can slide. Now, after they slide, those hills and valleys have been leveled off to a certain extent. So the friction that's required to keep something moving is less than this friction to start something moving because of this atomic effect. And so the coefficient of kinetic friction, moving friction, will be less than the coefficient of static friction. And that's the atomic description of friction.
And so it's kind of like the static friction is just sitting there already present, and that's why you have to use more of a force to get it started. And then once you get it started, it's just like the weight, really, right? And
Then it's
a little bit
smoother.
of friction.
It's once you get it started, you've chopped off some of the hills, and they fell into the valleys. I mean, I'm greatly simplifying all of this, but
Right.
that's basically what happens. It does become smoother when you push something, right? Because
Yeah.
that's
Once you
how
get
you
it
make
started,
something smooth. Yeah, that's the way you make something smoother, right? The way they grind a lens for your eyeglasses. It's just by a lapping machine, by rubbing surface down until it becomes as smooth as they want it. So yeah, pushing and getting something started requires that you overcome the force of resistance of these hills and valleys. Once you get it started and you knock those things down, some of them, not all of them, and you'll have less resistance. Then if you try to push it again, If you let it stop and push it again, it'll be easier. Why? Because the hills and valleys have been worn down by the first time you did it.
Huh, interesting. I would have thought if you stopped that it would have gone back to the beginning, but you've eroded hills and valleys by that point, I guess.
Yeah, you've eroded them. Yeah, that's a good point. A good way to express it. Eroded them. Or sanded them
Oh,
down.
yeah. Should we keep going?
Absolutely. Yo, Toby, we lost the screen.
I
There
think
we
I
go.
still have it.
Oh,
Are we back?
yeah.
We should be back now, right?
Yes, sir.
And Scott, so I think we do have at least one other person that wants to read. So you're free to keep going for a bit, but just do know we do have people on deck whenever you're ready to popcorn.
Okay, cool. Well, if we want to push ahead, I mean, I don't mind doing this next one, and then I'll give over if that seems cool, or I can
That
shift
sounds good
now,
to
whatever.
me.
Okay, let's go. 4.5 inclined plane. Now we're going to do the one problem that has sent more people away from physics than anything else. It is called the inclined plane. A lot of people who do not remember where they were during the Kennedy assassination say, I remember the day I saw the inclined plane. That's the day I decided I'm not going into physics. This is very bad publicity for our field. This guy's got a little comedic thing going too, it seems. You come into a subject hearing about relativity and quantum mechanics, and we hit you with this. So why am I still doing this? Because this is the entry ticket into the business. It is inconceivable to me that you kind of need to scroll. I don't know. I'm at the bottom of the page. I don't know about anyone else.
You said it is inconceivable to me that you, right?
Yeah, and that's the end of the line for me.
Is it? I wonder if
So
it's frozen for you, maybe.
Is it? I don't know. It's been doing fine.
Do you see me scrolling up and down right now?
No, I'm just that I'm
Does
an
anyone
inclined
see me
plane.
scrolling up and down right now?
Yeah, I can see it. Yeah.
Okay.
Leave
Maybe
the thing
try
and rejoin, Scott.
rewatching, Scott. Like exit it and then pull it up.
Right. Okay, I'm still it is inconceivable to me that you
Is it inconceivable that you could understand more advanced topics without being able to understand this one?
No, I'm still frozen there.
I can reshare it. That might help.
Yeah, are you sharing through your webcam, Toby, or are you sharing screen
No, I was
sharing?
doing it normal.
Oh, okay. Weird. Yeah, it's working fine for me. I'm not sure what's going on.
It looks like it's working now too. Yeah,
Okay,
it is
cool.
oh shit. It is inconceivable to me that you could understand more advanced topics without being able to understand this one. Go ahead and mock the inclined plane, but only after you can prove you have mastered it. Here is the notorious problem. There is a mass M sitting on a plane inclined at an angle theta as shown in the left half of figure 4.3. We know it's going to slide down the hill, but we want to be more precise. The whole purpose of Newton's laws is to quantify things for which you already have an intuition. The novel thing about the inclined plane is that for the first time, we are going to pick our x and y axes not along the usual directions, but parallel and perpendicular to the incline. What are the forces on this mass? I have told you first deal with contact forces. But the only thing in contact with the mass is the plane. In general, the inclined plane can exert a force along and perpendicular to its own surface. But I'm first going to take a case where there is no friction. By definition, the plane cannot exert a force along its own length, so it can only exert a normal force, N. Then there's only one other force, the force of gravity, that we agreed we have to remember. I just have a question that just occurred to me, if I might ask. Like thinking of breaking down gravity into the X and Y early physics. Is there a Coulomb equivalent to doing this sort of thing? Or should I just swallow that question and keep reading? Or
Shane, our resident Coulomb expert, equivalent master,
Is that Coulomb equivalent to everything?
indubitably, sir.
Yeah, but I don't know about the
this
specific
whole thing
math.
is being premised on gravity. It would be nice to start seeing how it would work differently. But okay. All right, here we go then. Even though the Earth is not touching this block, it is able to reach out from down below and pull this block down. These are the two forces in the mass will do what these forces tell it to do. And okay, first, I have to take this mg pointing down and break it up into components along my x and y axes. That's called resolving the force into various directions. Now, the key to this is to know that this angle theta of the plane is the same as the angle between vertical and the normal to the plane. You have to agree that if I draw a line perpendicular to the horizontal and I draw a line perpendicular to the incline, the angle between those two perpendiculars will be the same as the angle between the two lines with which I began. This is because, quote, make perpendicular means, quote, rotate by pi over 2. If you rotate both lines by pi over 2, the angle between the rotated lines will be the same. The vertical is perpendicular to the horizontal and the normal perpendicular to the inclined plane. Once you understand that, the rest is easy. So here are my equations. mg sine theta equals m times acceleration in the x direction. The normal n minus mg cosine theta equals mass times acceleration in the y direction. Now we know that this block is sliding down the incline. It's not going into the plane and it's not flying out of the plane. That's the reason we measure our y coordinate perpendicular to the plane. It does not change, unlike the traditional x and y, both of which do. So a of y equals 0 in equation 4.17, which implies n equals mg cosine of theta. Then you come, which will give you 0. Then you come to equation 4.16. We cancel m and read off the answer. Acceleration in the x direction equals gravity times the sine of theta. That's the big result, that the mass will slide down the hill with an acceleration g sine theta. This provides a good way to measure g, because if you drop something vertically, it falls too fast for you to time it. But if you let it go down an incline, by making theta very small, you can reduce the acceleration by a factor of sine theta. Here's another thing I should tell you right now. The professionals don't put in numbers until the very end. So if you're told the incline is an angle of 37 degrees and g equals 9.8 meters per second squared, don't start putting numbers into the first equation. I know for some of you it's traumatic to work with symbols. There are many reasons to work with symbols rather than with numbers till the end. First of all, if you've already put the numbers in and I suddenly tell you, hey, I was wrong about the slope. It's really 39 degrees, not 37. You're forced to do the whole calculation again. But if you use symbols to derive the formula for a of x and then ask me, what's your theta? You can just plug that in. Likewise, if I change the value of g because someone made a better measurement, you simply change g in the very last equation for a of x. You can also see if your answer had some mistakes in it. Suppose you got a of x equals g squared sine theta. You will know it's wrong because the units do not match. Maybe you have the trigonometry wrong. Maybe it's really a of x equals g cosine theta. You can do a few tests. For example, as the plane becomes less and less inclined, you have to get less and less acceleration. And when theta tends towards 0, so must the acceleration in the x direction, which must then be proportional to sine theta. Or if you make the incline almost vertical, the block is just falling under gravity with acceleration in the x direction equals g. The result a of x equals g cosine theta does not do that when we set theta equals pi over 2. Finally, a of x equals g sine theta is independent of m. That's an interesting property of the result you would not notice if you kept numbers everywhere. So we will agree to work with symbols until the end. Now we're going to make life a little more complicated by adding friction. shown in the right half of figure 4.3. Let the block be at rest and imagine there are some hinges on the inclined plane that allow me to increase theta from 0 to pi over 2. And everyone knows pi over 2 is like 90 degrees, right? I
do now.
Which I think it
Yep,
is.
because
Yeah.
well, in radians, right?
Yeah. Pi over 2 radians, but they're not even showing radians, so it looks kind of weird. 0 to pi over 2. Which equals, so pi over 2 radians. I want to know when the block will begin to slide down. Let me cut to the chase and write the equations. N minus mg cosine theta equals m times the acceleration in the y direction. Mg sine theta minus friction equals max. The first equation is the same as before and tells us that since a in the y direction equals 0, n equals mg cosine theta. And so long as I've done this, but cosine of 90 is it cosine of 90 is 0? Or cosine of 0 is 0? Anyway. In the second equation, do not write F equals mu Sn because the frictional force is not always mu Sn. It is whatever it takes to keep the block still up to a maximum of mu Sn. In other words, if theta is very small, the frictional force will in fact be a much smaller amount. F equals mg sine theta, which you get by setting ax equals 0 in the right-hand side. Let us crank up the angle to theta asterisk, beyond which it cannot stay still. At this angle, the friction is maximum, and we can assert mg sine of theta asterisk equals mu Sn equals mu S mg cosine theta asterisk, which gives us a way to measure mu S as tan theta asterisk. That was kind of nifty. Again, the mass cancels. So it doesn't matter how heavy a car you parked on the slope as long as mu S was the same. But G cancels too. So whether you park your car on the Earth or park it on another planet, the same restriction, tan of theta, is less than or equal to mu S applies. When we pass this limit, then the tangent of theta is greater than mu S, or mu sub S. The block will begin to slide down. It will now have a non-zero downhill acceleration because it is kinetic friction, mu of k times n, normal, that now opposes the velocity, and mu of k is less than mu of s. The operative equations are n minus mg cosine theta equals may, mg sine theta minus mkn equals max. What's the acceleration now? I take the y equation that says as before that n equals mg cosine theta since ay equals 0, and plug that into the x equation to obtain the downhill acceleration of the block. Mg sine theta minus mu k mg cosine theta equals max. G times sine theta minus mu k cosine theta equals ax. And I'm ready to pass the baton.
Awesome. Well, yo, thank you. That was some fantastic reading. Cool. Anyone? Anyone want to volunteer to read? All right. Sounds like it's me. Next is a problem of two masses, and m and what's that?
Yeah, so you want me to?
If you're down, sure. Yeah.
Yeah, I mean, I'll read a little bit. You want me to read a little bit? Why not? All right. So next is a problem of two masses, M and M, connected by a string that goes over a massless pulley mounted at the top of a frictionless inclined plane, as shown in figure 4.4. What can we say before doing the math? If M is greater than M, am I assured it'll go downhill? No, it depends on the angle. What is that symbol?
Theta.
Theta. Because only part of its weight, mg sine theta, is helpful in going downhill while all of mg is pulling m down. All we know for sure is that for a fixed theta, the bigger mass m will go down the slope as m to infinity, while the smaller mass m will go straight down as theta to 0. Let us figure out now when exactly the balance shifts. Anyways. Oh, hey. I recognize what this is. This is rigging. Hell yeah. Okay. Since we have two masses here, no choice of axis is going to make all their motions simple. M goes straight up and down while M glides along the slope. Let us ignore the boring n equals mg cosine theta equation for the y coordinate and focus on the motion along the plane. In the free body diagram, I have shown the same tension T wherever the rope is involved. For a straight massless rope, it is clear the opposing forces at the ends must have the same magnitude T, since there could be no net force on a massless object. For a rope that curves around the pulley, the explanation is more subtle, as I will explain momentarily. For M, the equation along the x direction is mg sine theta minus T equals ma. For the M, the equation in the up direction is T minus mg equals ma, where I have deliberately used the same A as in equation 4.29. I am not saying the acceleration of M and M are equal as vectors. They do not even have the same direction. Little m moves up and down while big M moves along the plane. By A, I mean the components of the two accelerations in the allowed directions of motion, defined to be positive. If M is moving downhill and M is moving up, this equality reflects the inelasticity of the rope. If M moves up 1 inch, M will slide down 1 inch along the incline. If the magnitude of the displacement is the same, so are the magnitudes of the velocity and acceleration. We can solve for A by adding equations 4.29 and 4.30 to obtain mg sine theta minus mg equals ma plus ma, which means A equals, Does this solution make sense? Now you notice that for A to be positive and for M to go downhill, it's not enough that M is greater than M. We need M sine theta is greater than M because only the force mg sine theta is pulling M downhill. The force mg cosine theta is trying to ram it into the inclined plane, and that's being countered by the normal force M. Can we use this formula when A is less than 0? That is, when M moves uphill. After all, I did all my analysis assuming it's going down. Yes, we can. All the forces I drew here, N, mg, and so on, are not going to change when you change the body's direction of motion. Gravity is always going to pull down whether the block moves with or against it. So once you have a formula for positive A, you can apply it to negative A as well. However, if friction is present, you cannot do that because you have to assume a particular direction of motion before you can assign a direction to the frictional force in the equations of motion. Now let's consider why the forces at the two ends of the rope emerging from the pulley have equal magnitudes, T. Assume that the pulley is massless and that the rope does not slip. That as the masses move and rope moves over the pulley is forced to rotate without relative slippage. In this case, the part of the rope instantaneously in contact with the pulley, and the pulley itself may be viewed as one rigid body. It is like a bicycle chain whose links mesh with the teeth on the wheel the pedal is turning. The tensions on the rope at the two ends are clearly trying to rotate this body in opposite directions, as is clear in the free body diagram in figure 4.4. If these tendencies are not exactly balanced, that is, if these forces are not equal in magnitude, they would produce an infinite rotational acceleration of this massless rigid body, just like a non-zero force would produce infinite linear acceleration on a massless object. By the no-slip condition, this means an infinite linear acceleration for the two masses, which is impossible because the masses are non-zero and have finite forces acting on them. So the forces at the two ends of the rope emerging from the pulley must have equal magnitudes. We will return to a proper study of rotations in the case of the massive pulley in Chapter 10. Note that even through the rotational effects of the two non-parallel forces cancel, their non-zero vector sum can produce linear acceleration of the pulley. The axle about which the pulley rotates provides an equal and opposite force to prevent this. Luckily, this last force does not contribute to rotations around the axle. 4.7 Circular motion, loop-the-loop. Now we'll turn to some interesting problems in circular motion of various kinds. The first, shown in part A of figure 4.5, describes a ride in an amusement park. You sit in these baby rockets hanging from a rope along with other petrified victims. The whole thing begins to spin, and the rope, instead of remaining vertical, starts tilting at an angle theta, which we want to determine as a function of the tangential speed v and radius r of the circular orbit. We apply force equals mass and start listing the forces on the baby rocket. Gravity provides the usual mg pointing down. The rope can only exert a force t along its length. Let us trade the tension along the rope for the sum of two equivalent forces. A vertical part. Tell me what that equation says.
T sub y equals T cosine theta.
Okay, okay, all right. In a horizontal part, Tx equals T sine theta directed toward the center of the circular orbit. The equations are T cosine theta minus mg equals 0 for vertical, and then T sine theta equals mass equals m over v2 over r, radial or horizontal. Which is velocity squared over radius. Anyways, in the first equation, we recall that by assumption, the rocket's orbit is a horizontal circle and it has no net acceleration in the vertical direction. In the second, we recall from section 2.6 that a body moving in a circle of radius r at speed v has a centripetal acceleration, v squared over r. So this is a case where we know A in force equals mass. Eliminating t, we find tangential theta equals velocity squared over r g. Is g gravity? What is g?
Yes.
Yeah.
Okay.
Downward gravity, the measurable one. I guess
Yeah, no.
technically the
I had to.
same,
I
but
remember a lot.
yeah.
It's funny. All of this was in my rigging book. Well, some of it was. Anyways, left an amusement ride in which you go around in a horizontal circle of radius r in a baby rocket. The rope supporting you necessarily makes an angle 0 equals tan minus 1 v squared over rg with the vertical. A car going around a circular racetrack of radius r at speed v, the road has a banking angle that obeys tangent theta equals v2 over rg. The normal force N has a horizontal part that gives the necessary force mv squared over r to bend the path into a circle. The symbol, which is center of gravity, is used in both parts to indicate that the rocket or car is going into the page away from you. The convention is based on how an arrow with feathers would appear going away from you. Likewise, I don't know that one, indicates an arrow coming out of the page towards you. It is worth finding the tension on the rope since our lives may depend on it. It is T equals mg square root of 1 plus the v squared over rg squared. Using t equals the square root of t2 over x plus t2 over y, here is another interesting problem. You are driving on a circular racetrack of radius at a speed v. Suppose the plane of the road is strictly horizontal, perpendicular to g. Some agency has to exert a force, mv squared over r, on the car to bend it into the circle. It is, of course, the road that does this. Thanks to the frictional force, F is greater than or equal to, I don't know that U, S, mg. What is that U?
Mu.
Okay. Directed toward the center. I used the whatever that is, the static coefficient, and not. What did you say that was?
Moo. Like moo cow.
Okay, all right. I don't even know what that is. Okay, that's beyond me. All right, moo. Where was I at? Okay, and not mu. K. I don't know what little k is. Oh, kinetic. Mu kinetic. The kinetic. Well, even though the car is moving, because we are discussing the force in the radial direction and the car has no velocity in that direction unless it is skidding. Note also that the car does not really have to travel in a circle. All we need is at this instant, the trajectory is part of some circle of radius r. If you don't have the requisite static friction, if mu little s mg is less than m v squared over r, your car will not be able to make the curve. It will fly off. But there is a clever way in which you can still make the turn without any friction, and that is to bank your road by an angle theta as shown in the right half of figure 4.5. Imagine now you're going into the paper. The frictionless road only exerts a normal force N. Let us resolve that force into a vertical part, N cosine theta, and a horizontal one, N sine theta, directed toward the center of the circle. The equations are N cosine theta equals mg, 4.37, and then N sine theta equals m times v squared divided by r, 4.38. Eliminating N, we find the banking angle to be tangent theta equals v squared divided by rg. Let me elaborate. You want the car to go around the bend at a certain speed. If you bank your road at that angle, you don't need any friction to make the turn. Even though the frictionless road can only exert a normal force thanks to banking, a part of the normal force points towards the center, providing the requisite centripetal force. Of course, when you drive on a real road, you do not have to travel at exactly the speed for a given r, for any small differences will be made up by the frictional force of the tire. It is just that you do not want to rely on friction for the entire radial force. Finally, the famous loop-the-loop problem, which defies common sense, is shown in figure 4.6. You come down on a roller coaster track from some height of h, you go in a vertical circle, and for a while you were upside down. The eternal question is, why don't you fall down? We'll find we can understand this phenomenon fully with Newton's laws. The forces on the coaster are mg acting down on the force of the track, which has to be normal to it since it is assumed to be frictionless. But it too points down. We are doomed. Why don't we fall? The answer is that we do fall. That is, we accelerate downward, but this does not mean we get any closer to the center. The two forces mentioned combine to bend the coaster into a circular path and produce the requisite downward centripetal acceleration. And this is how your center of gravity stays. Anyways, never mind. The roller coaster comes down from a height of h and goes into a loop in the vertical plane. Why does it not fall down? The forces on it are mg acting down and the track force n also acting down. It does fall. As explained in the text, the three arrows forming a triangle in the inset show the initial velocity v minus, what is that symbol?
Delta V over 2.
The velocity minus delta v over 2 just before it reaches the top, the change delta v in a small interval near the top, and the final velocity v plus delta v divided by 2 just after it passes the top. Anybody else want to take over?
Yeah,
Sure.
I got you.
Oh, go ahead, Alan.
So just after it passes the top, given by equation n plus mg equals m nu squared over r. Solving for n, we find that n equals m nu squared over r minus g. If n comes out positive, then if n comes out positive, that is, points down to our convention, which happens if nu squared r is greater than g. We are safe. If it comes out negative, then we're doomed, as given in equation 4.42. It means that the track exerts an upward force, which is impossible unless there is some other mechanism, like a T-brake, that goes under the track and supports the coaster, even if it's hanging upside down, or just as we're hanging upside down. I believe such a thing exists in real roller coasters in case they get stuck at the top or do not go fast enough. In our idealized roller coaster without any backup, the velocity obeys equation 4.3 to safely make the loop. We will figure that the minimum height of we will figure out the minimum height from which it must be released to satisfy the conditions when we derive the laws of conservation of energy. Let us be sure that we understand again why accelerating down does not always mean gaining speed towards the Earth. If you drop an apple, accelerating down means really picking up speed towards the ground, towards the center of Earth. To start with is, depending on your how much you want to deflect the old vertical to be perpendicular to the equigravitational potential of the G-wave. So if you drop an apple, it starts with a zero vertical speed and picks up speed. In our example, the coaster is accelerating, but the tiny change in velocity and change in a tiny time. Change in velocity in a tiny time. All right. Which radially points down in figure 4.6 near the top of the loop. It is now added to a huge horizontal velocity pointing to the left. We will now see that this implies the velocity has a constant magnitude in changing direction. Consider the impact of adding a tiny change to delta v to the velocity, delta nu, with the velocity nu of the magnitude of velocity. Assume delta nu can be in any direction relative to nu. The resultant velocity has a magnitude squared given by equation 4.4 to equation 4.7. And then finally, we're going to end on 4.48. To find the d nu squared over dt, we keep the term linear in the delta nu. This equation generally implies the non-zero rate of change with the magnitude of nu unless the delta nu and the acceleration a are perpendicular to nu, as in the case of circular motion. So here we got the old diagram for the circular motion. 4.7, you fire 2 bullets from a tower at increasing speeds, which land farther and farther away, points 1 and 2, beyond a circuital speed. the bullet would go in orbit. If
Critical.
Critical. Is it? Okay, thank you, sir. Beyond a critical speed, the bullet would go into orbit. It is, of course, never ceased to accelerate the Earth, or accelerate towards the Earth. All right. So a little later, the total velocity vector merely gets rotated with no change in length and becomes the tangent to the circle at a slightly different point, going around in a circle in the example of constantly accelerating towards the center, but not getting any closer to it. Scroll down a little bit and get some water here. Here's another example of this phenomenon. Suppose you're on a tower and you fire a gun horizontally, as shown in figure 4.7. The bullet hits the ground at point 1 under the pull of gravity, and you fire another bullet at a greater velocity and it will land a little further away at point 2, while greater initial speed will extend the flight time, will extend the time of flight. Even on a flat Earth, the flight time is further enhanced by the curving under the bullet. There will be a certain speed at which the bullet will keep falling, but will not get any closer to the center because the Earth is falling under it just as fast. It is in orbit, as shown in these shown by the circle. That is how, in fact, you launch a bullet into orbit. So what's the first thing you should do when you fire a gun? Move away, because it's going to come back in about 48 minutes and get you from behind at 17,650 miles per hour. Just thinking of looking through a telescope and seeing a photon that goes around the Earth. You see it, Anyway, this calculations assumes that there is no atmosphere, which of course leaves you with the even more pressing problem.
All right.
Chapter 5.
Do you want to get into chapter 5, or should we call it for the night?
Let's see. We're an hour and 30 in. Oh, Eric were you trying to read tonight or what? No, Eric's not even here.
Yeah, we lost Eric. We lost Bennett. I think maybe we just take a few moments to chill out and then call it, I say.
Sounds good to me.
Cool. So yeah, first of all, thanks Eliyah and Scott for reading. That was awesome.
Yeah, dude, much appreciated. You guys killed it.
Yeah, that was really cool. Piezo, you missed Bennett, man. I tried pinging you.
Oh, it's cool, bro. I mean, I responded to you. I just was busy at the moment.
Nah, I figured. We just finished reading physics.
What are you in here saying?
I mean,
well, we went over some Sagnac originally and where Einstein's equations apply. The old closed polygonal circuit. So that was cool. And then we went over the physics book.
Oh, we talked about the old extension of a polygonal circle to infinity equaling a straight line.
Yep. And then, the uniform motion, all good or whatever.
The good old uniform motion being equivalent to an inertial frame at rest, and then extending a circuit to a line, and then now you've got a line at rest and a non-moving frame.
Something like that.
Something like that. I got you, Bree.
Well, cool. I guess. Have any other final thoughts, questions before we wrap up streams?
No, I think when he broke down the atomic structure stuff, I thought that was really interesting. The hills and valleys making an interlocking structure to provide the resistance, and then as it's moving, you've kind of chopped that off, so it's less. That was really helpful.
Yeah, it was super interesting.
Can you elaborate?
Well, you can go watch it.
Yeah.
Or you can try and run it down.
Yeah, so you got your desk, right? And then you got your cell phone. So you got your phone on your desk and you think like, oh, okay, your desk is pretty flat and smooth. Your phone case, it's pretty flat and smooth. But when you examine them closely, right, on the atomic structure, they're actually like, rigid, or not rigid. They actually have hills and valleys, from their molecular structure. And the interlocking of the of that structure, of the table and the phone together provide that resistance that you have to overcome to get it to move initially. And what he was saying was, when it's locked together, it has the most resistance possible. And then after you overcome that, you're essentially grinding off the hills and valleys, and it requires less motion or less force to keep it in motion because you've degraded those hills and valleys or whatever. So it was just a nice way to break it down.
The overcoming the moment of inertia.
Yes.
Yeah. Yeah, I mean, if you think about it, as molecules as a bunch of little orbs, right? If you got a bunch of little orbs touching each other, right? Like the tops of those orbs are not actually going to make a flat, smooth plane either. There's like a little divot from one orb to the next.
Right.
And so if you move across it, right, you will actually like have like variations in the repulsion or the forces, or you'll have friction actually.
Yep. Yeah, that's what we were covering specifically. Actually, they were adding friction into the kinematics. Well, actually, I guess they were getting a little dynamic with it since they were adding that. But yeah, that's what they were going over and how that would change things.
Yeah, you got to learn the idealized stuff first to see how to do it, and you got to add in all the other variables.
Yep. Yeah, that's actually what this whole section was about. Was the introduction to that.
Yeah.
If you want to continue, oh, dude, homie's down to keep reading, dude. I don't know. Is this a continuation, or are we about to learn about the conservation laws?
Who? I'm down.
Oh, you want me to pull it back up?
I mean, pull it back up. The man said he's ready to read a PDF, dog. I'm not going to stop him.
You thought we were done, listener? You thought this was over? You were looking at the timer on YouTube or Rumble, and you're like, this is over? And then you already know because you looked at the timer that this is not over. We got more reading to do. Go ahead and pull it back up. All right.
When we gonna cover the Schrodinger lectures, bro?
When you get back from your vacation, yes. I want you to be there specifically, and I really want to go over them myself.
Right now, I just got home. My vacation doesn't start till tomorrow, bro.
Oh, dude. So, I mean, trying to get lectured up or what?
And I'm trying to hear what Schrodinger had to say about these waves, dog. But don't let me interrupt your guys' physics stuff. Physics was cool.
Yeah.
Y'all let me know whenever y'all are ready.
Yep. We'll start us off whenever you're ready, sir.
Yeah.
For the conservation of energy.
Okay. All right. Here we go. We're at Chapter 5, the Law of Conservation of Energy. 5.1, Introduction to Energy. The law of conservation of energy is a robust and powerful one. When the laws of quantum mechanics were discovered in the subatomic world, many cherished notions were abandoned. You must have heard the ugly rumors. Particles do not have a definite position and definite velocity at a given time.
Unfounded rumors. Sorry.
They don't move along continuous trajectories. You might think the particle must have had an interpolating trajectory connecting two sightings, but it does not. And to assume it does causes conflict with experiment. While many of the ideas of Newtonian mechanics were abandoned, the notion of a conserved energy survived the quantum revolution. There was a period when people were studying nuclear reactions, and the energy they began with didn't seem to be the energy they ended up with. Niels Bohr, the father of the atom, suggested that maybe the law of conservation of energy was not valid in quantum theory. Then in 1931, Wolfgang Pauli decided to put his money on the law of conservation of energy. He postulated that some other tiny electrically neutral particle which escaped detection was carrying away the missing energy. That was a radical position to take in those days, when people did not lightly postulate new particles, as compared to today, when if you don't postulate a few new particles, you don't get your PhD in particle physics. Pauli's particle, called a neutrino, was detected after many, many years in 1959 by Claude Cohen and Frederick Rains. Nowadays, neutrinos are one of the most exciting, elusive, and mysterious things one could study, and they hold the key to many puzzles concerning the universe. Let's see how the notion of energy conservation arises, starting with one dimension. When a force acts on a body, it changes its velocity. In one dimension, this simply means speeding up or slowing down. We're going to find the relation between the speed accumulated when a force acts on a body for some time and the distance the body has traveled in that time. Consider the case when the force F is constant, not varying with time. That produces an acceleration. Acceleration equals force over mass. In the first chapter, we learned that if a body has constant acceleration A, v squared equals v squared over 0 plus 2a x minus x 0. 5.1, where v and x are the current velocity and position, and VO and XO the corresponding initial values. In those days of kinematics, we didn't ask, why does it have a constant acceleration? We were just told it has a constant acceleration. Just find out what happens. Now that we have learned dynamics, we know acceleration has a cause, namely some force. So I'm going to replace A by F over M and make one more cosmetic change in the notation. All the initial final quantities will carry a subscript 1, 2, then equation 5.1 takes the form v
If you
squared over
want, hey
2
yo, if you
equals.
want, Eliyah, you can always just say equation 5.2 and not read the equation if you don't feel like it. But if you want to, that's always cool too.
I would prefer to say the equations if I actually had an index next to me so that I could know what all of them are. But without that, I mean, the equation looks weird. So I'll just say 5.2, where
Cool.
d equals x minus xo equals x squared minus x1 is the distance traveled during this interval. 5.2, the work energy theorem and power. Equation 5.2 says that when the force acts on a body, it changes the velocity, and the change depends on how far the force has been acting, on how many meters it has been pushing the object. The change is not simply in velocity, but in velocity squared. Let us move everything involving the force to one side and the particle to the other side. 5.3. The combination half mv squared is called kinetic energy and is denoted by K. The product FD is called the work done by the force and is denoted by W. The units of W are Newton meters, and we replace that by joules or J. We have found the simplest version of the work energy theorem 5.4. What if there are 36 forces acting on the body? Which one should I use? Say I'm pulling and you're pushing. Then F has got to be the net force because Newton's law connects the net force to the acceleration. If you and I have a tug of war and we cancel each other out to 0, then there's no acceleration, and the body with some initial velocity will maintain its initial velocity. The work energy theorem says the change in kinetic energy is equal to the work done by all the forces. In this case, there is no change in energy, though there are two forces at work that cancel. It turns out that it is sensible to define the work done by me, which is equal to F times the distance traveled, and the work done by you, which will be given an opposite sign. When we do attach a plus sign and when we do attach a minus sign, if you go back and review the whole derivation, you will see it was misunderstood that A was a positive quantity. Then everything works. If the body is moving to the right and I am pushing to the right, then the work done by me is positive. And if you were pushing to the left and the body still moved to the right, the work done by you is negative. In other words, if you get your way, if things move the way you're pushing, the work done by you is positive. If the object is moving counter to your will in the opposite direction to your force, the work done by you is negative. I'm lifting this piece of chalk at constant velocity from the ground as kinetic energy is not changing. That means the total work done on the chalk is 0, but not because there are no forces on it. There is gravity acting down, and I am countering gravity with exactly mg. The work done by me is positive because I want the chalk to go up. And it does. If it goes up by an amount h, the work done by me is W equals mgh. The work done by gravity in the meantime is minus mgh, and the total work done is 0. Let us imagine all of this occurs in a time at delta t, and the distance moved is d equals delta x. Then if you divide both sides of equation 5.4 by delta t and take all the usual limits, 5.5, where p is defined as the power. So power is the rate at which work is done. For example, if I climb a 12-story building, I have done some work. My mg times the height of the building. I can climb the building in 1 minute. I can climb the building in 1 hour. The work done is the same. But the power is a measure of how rapidly work is done. That's why it's the product of force and velocity or work divided by time. The units for power are joules per second. That also has a new name, which is watts or just W. You may use a kilowatt or kW, which is 1,000 watts. So if you have a 60-watt bulb, it's consuming energy at the rate of 60 joules per second. Now let's turn to the next generalization. When the force is not a constant but varies with x, do we know any example of a force that varies with x? A springing is a good example with Fx equals negative kx. Even gravity is a good example if we consider large distances. I think it is no secret that the force of gravity is mg only near the Earth, and that if you go sufficiently far, you will notice gravity itself is getting weaker. It will still look like mg locally, but g won't be a fixed 9.8 meters squared, negative squared. It will be decreasing as we move away from the Earth. What is the work energy theorem when the force varies? Let's draw ourselves a force, fx, that varies with x, as in figure 5.1. I'm just taking any function of x that I want. Now the acceleration is not constant because the force is not a constant. We cannot apply the formula watts equals fd because f varies over the distance d. So we resort to the usual trick in calculus. Find an interval of width dx that is as narrow as you want so that during that period f is essentially a constant equal to fx. The value of f at x for that tiny interval, I can still say that the change in k is figure 5.6. You show them all that. Woohoo. Geometrically, fx dx is the area of the thin rectangle whose base is dx and whose height is the function f at that x. If fx is less than 0, the area is counted as negative. If you eventually went from x1 to x2, then the work done by the force is given by the area under that graph in the sense of calculus. In every segment, you pick up the change in kinetic energy, dk. You add it all up to get k2 minus k1 from the left-hand side. The right-hand side is the integral of the function fx between x1 and x2. The general work energy theorem now says, figure 5.7. Yeah. Even if you have never heard of an integral, if I give you a function, you can still deal with this problem. You'll come to me and say, give me your function. I'm going to plot it on some kind of graph paper with a grid on it. And I'm just going to count the number of tiny squares enclosed. That's the area, and that's the change in kinetic energy. So integration is just finding the area bounded by the function at the top, the x-axis below, and two vertical lines at the starting and ending points, x1 and x2. Now, here is a little digression, a 3-minute introduction to a great secret for finding the area. If you give me a function and you tell me to find the area under it from x1 to x2, I can show you a trick. You don't have to draw anything on graph paper. First, I find a function gx specified by its derivative, 5.8. Then I claim, and will prove shortly, that 5.9. This is the opposite of taking derivatives. Now we want a function whose derivative is given to be f. If I say fx equals to the third, then gx is that function whose derivative is x cubed. Now I know I have to start with x to the fourth because when I take derivatives, I will lose a power. But I will also get an unwanted 4 in front. I fight that by putting a 4 downstairs and find gx equals x to the fourth divided by 4. You might point out that if you have a function whose derivative is something, adding a constant doesn't change the derivative. Then you can say, well, we are in trouble now because the world cannot agree on what g is. Because if I have one g, you can get another one with a different constant. But the beauty is that when you take gx2 minus gx1, this difference in the choice of c goes away. So most of the time we don't bother with the constant. Sometimes we make a special choice that recommends itself. As you will see, when we study gravity on a celestial scale, the choice of constant is like the choice of origin in the projectile problem. Any origin will do, but it is convenient to choose it as the point of takeoff.
Oh, really?
Why is gx the function whose derivative is fx? Let us call the area from some arbitrary point x0 to the point x is gx. If I add a little more area out to x plus dx, the extra area is fx dx. This, by definition, is dg, the change in g. Dividing by dx and taking the limit, we see f equals dg divided by dx. How did different g's differing by a constant arise? By choosing different starting points, XO, from which to reckon the area, but whatever we choose for XO, the change in the area due to changing the upper limit, X, is always given by dg equals fx dx. My goodness. Conservation 5.3, conservation of energy. K2 plus U2 equals K1 plus U1. Bunch of math stuff.
You want me to
Uh,
help you with these equations, bro?
yeah.
What?
Okay.
Piezo's gonna read the equations.
Yeah, there you go. That's better.
Let us now incorporate what we've discussed so far and write k sub 2 minus k sub 1 equals the integral from x sub 1 to x sub 2 of f of x dx equals g of x sub 2 minus g of x sub 1 is equivalent to g sub 2 minus g sub 1, equation 5.10. We can rearrange this to give k sub 2 minus g sub 2 equals k sub 1 minus g sub 1. We now make a little cosmetic change and introduce the function u of x equals negative g of x, and f of x equals negative du dx. In terms of which we obtain the standard form, e sub 2 is equivalent to k sub 2 plus u sub 2, which equals k sub 1 plus u sub 1, which is equivalent to e sub 1. This is the law of conservation of energy. E equals k plus u, which is called the total mechanical energy, and u is called the potential energy. So total energy equals kinetic plus potential. Conservation.
Hey, Piezo, can you move a little closer to your mic or speak up a little bit?
Sorry, bro.
Okay, you're good.
Total energy is kinetic energy plus potential energy. Conservation of energy in physics has a totally different meaning from turn the lights off when you leave the room. Here it means that when a body's moving under the effect of this force f of x, even though it's speeding up and slowing down, a certain special combination, E equals 1/2 mv squared, because that's the kinetic energy, plus u of x, which is the potential energy, does not change with time. If you know the value of E at one time, then you know the value of E at all times. All right, there you go. You want me to finish this?
No. Oh, yeah, if you want, or I'll pick back up if you want. I appreciate that. I couldn't remember for the life of me how to say the words, but how to say the equation when it has parentheses. Of, of course. Anyways,
Yeah, in that notation, it's it just depends. But like in function notation, then a function with a parenthetical expression is like f of x, right? And then usually the subscript, you just say sub. And then if the subscript is 0, you usually say not. So like x sub 0 would be x naught.
okay. Mr. Engineer over here. All right, you want to keep reading, or you want me to pick it up?
I mean, I can, bro. I just didn't want to steal it from you.
Oh no, I like to share. All yours.
Okay. Let's consider a simple example. We take a rock and we drop it. We know it's picking up speed. We know it's losing height. So you may expect there's some quantity that's a combination of height and speed, a combination which doesn't change in this exchange. We can find that combination by this law. In the case of gravity, where F equals negative mg, the expression for potential energy U is U equals mg y, where y is the distance in the y-axis. Since it obeys negative du dy equals negative mg equals F. Now, the energy conservation law takes the form E sub 2 equals 1/2 mv sub 2 squared plus mg y sub 2. That equals 1/2 mv1 squared plus mg y1. That equals E sub 1. Now, in the mass and spring system, the corresponding relations are U of x equals 1/2 kx squared, since it obeys negative du dx equals negative kx equals f of x. And the conservation law assumes the form E sub 2 equals 1/2 mv sub 2 squared plus 1/2 kx sub 2 squared equals 1/2 mv sub 1 squared plus 1/2 kx sub 1 squared equals E sub 1. So let us put that to work. If I'm going to pull the mass by an amount A, and I'm going to let it go, I want to know how fast it'll be moving when it comes to some point, let's say x equals 0. If you go back to Newton's laws, this is a pretty complicated problem. Think about why. You start with a mass that's at rest. If you pull it by an amount A, then a force negative Ka initially acts on it. That will produce an acceleration, negative Ka over m, which will give it a small negative velocity by the time that it moves a distance delta x to the left. But once it comes to the new location, a different force will be acting on it, because the x is now different from A. So the acceleration during the next tiny interval is different, and the gain and the velocity during that second interval will be different from that in the first, and then so on and so forth, of course. You have to add all these changes to find the velocity at x equals 0. That's a difficult proposition, but with the law of conservation of energy, you'll do that in no time. Let's do it, not just for x equals 0, but for an arbitrary x. we set x sub 1 equal to a and v sub 1 equal to 0 at the start. And we drop the subscript 2 on x and v at the generic point to obtain the generalized equation. 1/2 mv squared plus 1/2 kx squared equals 0 plus 1/2 ka squared. At the initial time, all the energy is potential energy. There is no kinetic energy because there's no motion. At any subsequent time, we can solve for the velocity at any location x. If you want x to equal 0, that's very easy. 1/2 mv squared plus 1/2 k times 0 squared equals 0 plus 1/2 ka squared. Now the 0 cancels out on the left. You rearrange the variables, you get v squared equals ka squared over m. That simplifies to v equals plus or minus the square root of ka squared over m. And that's, you pull out the a, that equals plus or minus a times the square root of k over m. And that simplifies to omega. So it's plus or minus omega a. We get two answers because the mass may be going past the origin in either direction, positive or negative direction. If it's passing the origin for the first time, it'll be moving to the left with negative velocity. Now for the case of a general x, equation 5.1 tells us v of x equals plus or minus square root of k over m times the square root of a squared minus x squared. You can see why finding the velocity is so much easier now. It's because we've calculated the kinetic energy change produced by the spring between 2 points, x sub 1 and x sub 2, once and for all, by doing the integral of the spring force and encoding that in u of x sub 1 minus u of x sub 2. Now let us take another problem. You got a mass hanging from the ceiling. Let's choose the origin of the vertical coordinate y at the lower end of the undistorted spring, so that the force due to the spring is negative ky. There will now be two kinds of potential energy, gravitational and spring-based, because there's two forces. So you end up with k sub 2 minus k sub 1 equals the integral from position y1 to position y2 of f of y dy. This equals the integral from y1 to y2 of negative mg minus ky dy, because that is the function. And then when we pull it out, you end up, or when you simplify that rather, you end up with mg times y sub 1 minus y sub 2 plus 1/2 k times y sub 1 squared minus y sub 2 squared, which can be written as k sub 2 plus mg y sub 2 plus 1/2 ky sub 2 squared equals k sub 1 plus mg y sub 1 plus 1/2 ky sub 1 squared. All right.
All right, I got a little lost in this math. So we're doing springs and gravity here, right? That's what this essentially is pulling the math for the forces of both, right?
Yeah, so you have an oscillation. If you'll scroll up a little bit, if you'll go back up a little bit more, up a little bit right there. So
it looks like a conversion of potential energy into a velocity when there is no velocity.
well, okay, they treat it the way they treat it, right? If something is not moving, then it doesn't have kinetic energy, right? Like, and if you've got gravity acting on it, but it's not actually moving, then they're considering it to have potential energy. Like, this is how much energy it would have if it was moving, type thing. And they use that to like balance everything out to make it the math work. It's potential energy is kind of a silly thing, like in a dynamic sense, but like by accounting for it, you're able to get both sides of the equal sign to work.
Basically, they equate how much velocity they could get if they removed one side of the equation. Like if you removed a load from the spring.
Yeah.
Cool. Okay. Excellent. Thanks, you guys.
Yeah, you also can think of it as like if you have an object sitting on a desk, take away the spring, like you just got a desk with like a brick sitting on the desk. The potential energy in that brick you could calculate based on like, you know, the effect of gravity being on it.
Yeah,
like
it makes sense.
If it was to fall to the floor, this is, you know, how much it would have, right? So anyways. How much further we got to go, just so I have an idea?
Let's see. Yeah, so we should probably finish out chapter 5 here. At least I would. Yeah, it looks like we're not far at all.
Okay.
You want me to go or you want to go?
I mean, I can do it, bro. I just wanted to know, unless you want to.
I don't know, by all means.
Huh?
Oh, you know you want to read those integral equations.
Yeah, I mean, um,
I mean,
I'm
if you
just,
want, yeah.
I'm looking at it. Are you real quick? Are you guys getting benefit out of reading the integrals out loud over and over again, or like?
No, you don't have to read them, dude.
Okay, well, I'm
I mean,
just
sometimes yes, but I would say usually no.
so
Yeah, sometimes
it might
yes.
it might be better to like explain kind of like what the integrals are for, right? Like, okay, if you see that squiggly line, let's look at 530. You see that squiggly line, right? It's got x sub 1 at the bottom and x sub 2 at the top. So when you're taking an integral, it's area under the curve. So what you're doing is you're imagining like a position, like a position curve, like from one point to another and all the points in between, an infinite number of points in between, right? So in that squiggly,
Keep going. I
in that,
was just
yeah,
gonna.
in that squiggly line, right? When you go from x sub 1 or x sub 2, you end up covering the entire space in between 2 points in space, like the entire area between 2 points in space. And whatever is inside that expression is evaluated across all those points. Because basically, if you didn't do an integral, the way that you'd have to calculate it is you'd have to plug in 2 points over and over and over and over and over and over and over again, and run it through the equation with 2 points over and over and over again. And the more points you put in, then the more approximately accurate it would become, and you would like get really close. But what the integral does is it infinitely approximates it to like the proper value. So that's how.
He's talking about finer and finer vertical slices of the area itself.
Yeah,
that you're
so
calculating as y moves from x point to x point.
I scrolled up here to highlight the since we're talking about integrals. He said here, you'll come to me and say, give me your function. I'm just going to plot it on some kind of graph paper with a grid on it, and I'm just going to count the number of tiny squares enclosed. That's the area, and that's the change in kinetic energy. So integration is just finding the area bounded by the function at the top, the x-axis below, and 2 vertical lines at the starting and ending points x1 and x2. So this is an oversimplified version of it, and what Piezo was just explaining would be something. I mean, really, you're taking. So what Piezo was explaining would essentially be taking a version of this, but you're infinitely going to smaller and smaller squares, so you can take a more and more accurate approximation of the area underneath, essentially.
Yeah, and instead of being an approximation, when you do an integral function, it's actually a solve. Like it actually gives you a precise answer. It's a solve, not an approximation, right? So it's the function that you do in order to get a solve for this area under the curve.
There you go.
All right.
I know why
And
I've seen
actually,
these
I think a
before.
lot of
These are the equations that matter when we're determining whether or not our rigging is going to hold up if something fails. I should have remembered these.
Integrals are used in literally everything. Any type of real world problem with like forces and bodies is, if you're not calculating something, anything that's not idealized in like one plane of motion or something like that is always going to end up using integrals pretty much. All right. Friction and the work energy theorem. One bad apple ruins the whole thing. Friction. Let's take a body with the spring force, which is negative kx, and a frictional force, little f, acting on it. I will try as usual to get a law of conservation of energy when friction is acting, and you will see that I will not succeed. It looks like everything here is watertight, right? You tell me all the forces acting on a body. I integrate each force from start to finish, and call that the difference of the corresponding potential energies, as I did in the case of a vertical spring mass system, which was subject to the spring and to gravity. So then I got my result, right? So here we go. K sub 2 minus K sub 1 equals the integral from x1 to x2 of f of x dx. That equals the integral of x sub 1 to x sub 2 of negative kx dx, plus the same integral of little f of x dx, okay? That ends up becoming 1/2 kx sub 1 squared minus 1/2 kx sub 2 squared, plus that integral of at little f of x from x sub 1 to x sub 2, f of x dx. This ends up, it just rearranges it, k sub 2 plus 1/2 kx sub 2 squared minus k sub 1 plus 1/2 kx sub 1 squared equals the integral from x sub 1 to x sub 2 of little f of x dx. All right, so makes sense so far. If we do the integral over little f of x, and we call that the difference of potential energies due to friction, we can take that to the left-hand side and get a formula for energy as a sum of k and two potential energies. So you got k plus the two potential energies equals this energy sum. Now, what's stopping me? Well, the answer is that the force of friction isn't just a function of x. It's not a function of just x. You might say, what do you mean? I'm pushing the mass and I know how hard it's pushing me back. But then I tell you push it the opposite way. Then you'll find the force of friction at the very same location is pointing in the opposite direction. This is unlike the force of a spring, which is going to be negative kx whether you're going towards the origin or whether you're going away from it. The same is true for gravity. Gravity is pulling down with the force negative mg, and it doesn't care whether the object's going up or whether it's coming down. At any given location, there's a fixed force. So the problem's not that the frictional force varies with x, but it's that the force is also a function of the direction of velocity, which can have either sign, positive or negative. So thus, little f actually equals f of x comma v of x. Let us postpone the evaluation of the integral over little f, and let us write it as this. Right? He just changed little f to little f of x comma v sub x, or v of x. All right, and then e sub 2 minus e sub 1 equals that integral. I cannot evaluate the integral of little f given just x sub 1 and x sub 2 because it can go from x sub 1 to x sub 2 directly, or it can go after one or more oscillations. So he's saying it's not always going to go straight from 1 to 2. It could like go back and forth on its way in between, and it could be moving a whole bunch in between, and I'm not going to know about it. So during these oscillations, the velocity will change the sign repeatedly, and so will the force of friction at any given x. So we must break down the total journey into segments wherein the velocity and little f have a definite sign at each value position of x. So every time we're at a position, in other words, every time we get to a point, we have to break down it into little segments where the velocity and little f have a fixed sign, like a positive or negative. We have to know every time we calculate the position. Here's an example where we consider just one segment within which v has a definite sign, and hence so does f. I pull a mass to the point x equals a, and I let it go. First, assume that there's a small amount of friction. I know that when the mass returns to the center, it won't be going quite as fast as it would be without friction. And I also know that when it overshoots to the other side, it will not end up going all the way back to x equals negative a, right? There's going to be some loss because of the friction. I want to find a prime, the coordinate of the leftmost point. For this leftward journey from x equals a to x equals a prime, the force is a well-defined function. F equals plus or minus, I'm going to be honest, I can't remember what that symbol's called off the top of my head.
That's mu.
Mu. Yeah, as soon as you said it, I remember. Mu sub k mg pointing to the right. The displacement is negative. D equals negative a minus a prime. And the work done by friction is work of friction, right? Work sub F, W sub F equals negative mu sub k mg or times a minus a prime. And that's all equivalent to negative F times or dot product of a minus a prime. And then he breaks this all down and gives you all the way to 537, where we have k sub 1 equals k sub 2 equals 0 at the start and the finish. This quadratic equation for a prime may be rearranged as follows. K over 2 times a prime minus a times this bracketed expression of a prime plus a minus 2 little f over k is all equal to 0. Now the root a prime equals a is trivial. That corresponds to the initial point where the kinetic energy is indeed 0 and the total energy equals the initial energy. Let us analyze the non-trivial solution. A prime equals negative a plus 2F over K. As we crank up F over K from 0 to A, whatever A is, then A prime starts to move rightward from x equals negative A and turns positive when we pass the point F over K equals A over 2. That is, the final point now lies at positive x. The oscillator never even makes it back to the equilibrium point. So, real quick before I go further, he's talking about like this spring, right? And they've got friction in the system. And because of that friction in the system, the oscillation is never going to make it all the way back to the original point. And as we increase that friction, like the amount that the oscillation returns on its way back is going to be less and less and less. And eventually, they're going to reach a point to where it never even reaches back to the midpoint. Okay, so it's going to reach like a critical dampening. So raising F further, we reach the limiting case F over K equals A, when the non-trivial solution coalesces with the trivial one. The mass never leaves the point x equals A, since the spring force at its very maximum of Ka exactly equals the frictional force. So this is where like the friction's so high you never get it to move. In this discussion, we assume mu sub s equals mu sub k. So here's the bottom line for the law of conservation of energy. You take all the forces acting on a body, and you equate k sub 2 minus k sub 1 to the work done, the integral of all the forces. Divide the forces into conservative forces, like a gravity force, a spring force, which depend only on the location, and on the non-conservative, like friction, which is the only non-conservative force that we will consider. The integral over each conservative force will turn into an associated potential energy difference. So let W sub F be the work done by friction. The final result will be E sub 2 minus E sub 1 equals the work done by friction, with E equaling 1/2 mv squared plus the potential energy at S plus the potential of the spring plus the potential energy of gravity plus the potential energy of whatever other forces are involved, where the potential energy US is due to the spring, UG is due to gravity, and so on and so on and so on. So scroll back up just a little bit, real quick, right there. So yeah, so if you look at 5.40, 5.40, you've got like this final energy minus this initial energy, right? E sub 2 minus E sub 1 equals the work done by the friction. So the difference, right? The difference in the energy is going to be equal to whatever work was done, because otherwise it would be balancing. This is the law of conservation of energy, right? We know like the energy is going to be the same. So if there's a change, and the change can be accounted for by some work done. In this case, it's being done by friction.
Thank you. Yeah, that makes sense.
All right.
Very
Excellent
nice.
recap.
Well, there we go. We are now on chapter 6 for next week or whenever we pick back up on this. We will be doing a conservation of energy in D equals 2. And then we'll start with a little calculus review there. Ooh, just in case you want a little sneak peek of what's to come. Ooh, we got some partial derivatives.
Ooh, bring your Texas Instrument 091,000.
Yep, don't forget it. Get ready for some nice partial derivatives, some more integrals. All right, so this will be fun. Cool. So yeah, thanks everyone. That will conclude reading night for tonight. Unless anyone has any final thoughts, any final questions, anything for the stream / recording.
Yeah, partial derivatives, you learn those in Calculus 3 or multivariable calculus, whatever you call it at your particular institution. So kind of like this stuff that we're going through in this physics, this is like without an understanding of calculus, it's kind of difficult to break it down into like a digestible form, because you see what's happening, but you don't really like get like why or how it's being utilized. So that's kind of why it's good to explain like what this function's doing, because you guys, if you haven't taken calc, you might not know how to do the integral, like how to evaluate it, right? How to perform the computation. But as long as you know like what it's doing, it will help you like digest what's going on, if that makes sense.
Yes. 1000%. And I appreciate that you took the time to explain things. Sorry when I scrolled up on you at that part. I didn't know if you. I guess you were probably about to go through the whole equation, so my bad on that.
No, it's okay. I wasn't going to go through every single thing. I was trying to look at one particular equation to use it as an example, but it's okay.
Gotcha. Cool. Well, yeah. Much appreciated. I love talking about this stuff, so kind of fun to have math talk night, essentially physics
Dude,
and math.
calculus was invented in order to be able to solve physics. Like that's the reason it even exists.
Yeah.
But like when you learn calculus, you don't learn it attached to physics. You learn it in like this like separated, like pure analytical theory, like pure math form, and it's like kind of annoying because without having a real world application, depending on the way your brain works, it might not make as much sense. That's why I like physics like so much better than I do math.
It's sort of like sex ed in grade 5.
Right. Like I think if they were to teach calculus by using physics to teach it, it would be like way better instead of separating it all. Like if they were
It
to
is
just
odd. Yeah.
if they were to like put them into one class, right? Like combine all the calculuses and all the physics into like one class and just slow the pace down, right? I think it would be better personally, but I'm not, the person who makes university curriculum, so.
I do agree. It's also just like, I think just from the student's perspective, it's just not real like intuitive. It's like, oh, so I got to take this class, this calculus class, but then I'm also going to take physics, which is basically a calculus class.
Well, it's a lot more. It's just you like, okay, calculus 1 is all about derivatives. Calculus 2 is all about integrals. It's literally calculus 1 is learning what a derivative is and how to do them. Calculus 2 is learning what an integral is and how to do them. Entire semester. That's what it is. And then you get to physics and it's like, oh, by the way, like here's an entire list of all the kinematic equations. You're going to use all of these, and some of these you're going to have to use with integrals in real world situations. So take that entire semester that you just spent an entire semester learning of how to do an integral, and that's just a common function you're going to do in like every other problem. So
Well, don't forget limits, because you forgot your Calc 1. You start with limits so that you can explain what the derivative is doing.
Yeah, I mean, yeah, okay. You're fair enough. Fair enough. You go through limits. I'll go ahead and tell you, you're never gonna really encounter limits again until, because I mean, you're just gonna do derivatives. You're never really
No,
gonna
yeah, it's
encounter
really just
limits
useful for
until
understanding what a derivative is doing, essentially.
right. The next time you're probably gonna encounter limits after like the breakdown in Calc 1 before you start using derivatives is maybe when you do Laplace transforms in differential equations, and then even then it's just like more just a formalized notation more than anything.
Well, it did pop up in a Gallup paper, if I recall correctly.
Yeah, I mean, if you think about like doing position functions, right? You can like think of those in terms of limits, like infinitely approximating stuff so that you can't actually solve for, because that's what a limit is doing. But like, just rarely are you going to use them. I'll just put it that way.
No, it makes sense. Well,
Oh
cool.
no! Did you ever have to use limits very much, Stone, in your work? I mean, it's pretty much derivatives and integrals like all day, every day, right?
No, not at all. No, really. I mean, past a few area calculations here and there, but they're quite minimal. A lot of our stuff has a lot to do with electromechanics, and I don't, I don't see that used much at all.
Yeah. Yeah, that's what I figured. But I mean, yeah, you're right though, Toby. You learn what limits are in order to be able to understand what the point of a derivative is. Because basically when you do a limit, you're doing like you're doing a calculation, like a computation by hand, and it's like a little bit more drawn out. And then when you just learn what a derivative is, you're like, oh, there's just this rule I can follow that shorthands all of that into like a 5-second calculation, and I don't have to do any of this. Cool.
Yep. But it's conceptually pretty useful, I think. Or at least according to math teachers, it seems to be.
Yeah. Well, when you're doing derivatives, you're doing limits essentially, right? I mean, that's like what you're technically doing. It's just like not how you're evaluating it. You're doing um,
Yeah,
the
from both
derivative
sides.
function.
Yeah.
You're accomplishing the same thing that you would have accomplished with a limit approximation, except as a discrete function. That's a good way to say it, I guess.
Oh yeah, that sounds good. Sounds good to me. Well, cool. Should we close out the stream? Any other final thoughts? Any other questions? Anything? All right then. Thank you everyone for tuning in for Reading and Research Night. Tune in tomorrow night for episode 100 of Flat Earth Fridays, hosted by Sacred and Proud. I believe Space Audits will be streaming that, probably ADL as well. So check that out. And shout out to them for doing 100 weeks of Flat Earth Fridays. So yeah, check that out, and then check us out next week for more presentations and reading and other fun things. Take care, y'all.